All right, so you're getting ready for that senior software engineer interview, and congrats. I've been there, done that, and let me tell you, even with years of experience, those interviews can be tricky.
Yeah, for sure.
Today, we're taking a deep dive into something that might surprise you, the evolution of databases. You might be thinking, what does database history have to do with me landing my dream job?
Yeah, right.
Well, trust me, understanding this journey can give you an edge, especially when those tough data modeling questions come up.
Absolutely. We're going to trace the path from the dominance of SQL to the rise of NoSQL, and you'll see how these concepts that can seem kind of abstract actually translate into real-world interview scenarios that you might encounter.
Okay, let's unpack this. So SQL, it's practically the bread and butter of the database world, right? But how did it become so common? I mean, its roots are in things like transaction processing systems, things like airline reservations, not exactly the stuff of Silicon Valley dreams, is it?
Well, it's fascinating. SQL's dominance really comes from its elegance in simplifying complexity. Back in the 70s, working with databases meant grappling with the details of physical data storage, a real headache.
Yeah.
SQL came in and it abstracted all that away, providing a cleaner, more intuitive way to interact with data. And that ability to abstract, that's a core principle in software engineering, something any seasoned engineer like yourself should appreciate.
So SQL was like this huge sigh of relief for developers, streamlining things in a big way.
Mm.
But then came NoSQL kind of disrupting everything. What prompted this rebellion in the database world?
Well, the tech landscape was undergoing a massive shift. Huge data sets, applications demanding super fast responses, and the need for scalability that traditional SQL systems sometimes struggled to deliver. So NoSQL databases emerged as a response to these challenges, offering greater flexibility and the ability to handle those massive data loads, especially for applications with high write throughput. Plus, there was this growing preference for open source solutions, something that resonates with a lot of developers.
That makes sense. So now you've got these two powerful forces, SQL with its structured approach and NoSQL with its flexibility. But now we get to the really interesting part, the infamous impedance mismatch.
Ah, yes. A classic conundrum. Imagine you're building an application like LinkedIn, and you need to represent a user's resume in your database. On the one hand, you have object-oriented code, thinking in terms of objects, classes, relationships, and then on the other, you have your relational database with its tables, rows, and columns. Trying to map between these two worlds can be a real pain.
Yeah, I can see how that would be a challenge, especially with data as complex as a resume. You've got multiple job entries, different skills, education history, all these nested elements.
Exactly. Think about representing work history. Each job has its own set of details: the title, the company, dates, maybe a description. In a relational database, you might end up with multiple tables linked by foreign keys, not exactly elegant. And what happens when the requirements change and you need to add a new field? It could mean altering several tables and potentially migrating data, a process that can be slow and disruptive.
Yeah, yikes. That sounds like a logistical nightmare. So how did developers tackle this impedance mismatch?
Well, there were several approaches. Early on, SQL databases introduced features like structured data types and support for XML to try to allow storing multi-valued data within a single row. But then JSON emerged, offering a seemingly more elegant solution.
JSON, the darling of the web development world. Yeah, I can see why it would be appealing for representing complex data structures.
Absolutely. JSON, with its document-like structure, seemed like a perfect fit for handling these intricate nested data structures. Instead of splitting your resume data across multiple tables, you could represent the entire thing as a single JSON document.
Okay, so that means fetching the entire resume becomes much simpler. One query and you've got it all. But I'm guessing JSON isn't a silver bullet, is it? There must be some trade-offs.
You're absolutely right. Every solution has its nuances. One concern, especially in the early days of JSON's adoption within databases, was the potential lack of schema enforcement. You could have variations in data structure within a single collection, which could lead to inconsistencies and make data management more challenging. Have you ever worked with a system where the data format suddenly changed without warning? It can be incredibly frustrating to deal with.
Yes. Trying to wrangle data with unexpected format changes is like trying to fit square pegs into round holes. Not fun at all. So while JSON addressed the impedance mismatch, it also opened up this whole new set of challenges around data consistency and the potential for errors.
Precisely. And this is where understanding the historical context can be really helpful. The challenges faced by document databases, particularly in managing complex relationships, weren't entirely new. They actually mirrored problems encountered by early database systems like IBM's IMS back in the 70s.
Wait, really? Are you saying we were essentially reinventing the wheel with these new NoSQL solutions?
In some ways, yes. The hierarchical model used by systems like IMS shared some similarities with the document model in NoSQL databases. Both worked well for one-to-many relationships. Think of a user and their multiple job entries. But when it came to many-to-many relationships, things got complicated.
Okay, so give me an example. How would these older systems, or even some document databases, handle a scenario like mapping skills to users? Where many users can have the same skill, and one user can have multiple skills.
That's a perfect example. In a relational database, you'd typically use a join table to represent that many-to-many relationship. But early hierarchical systems, and even some document databases, didn't have good support for joins. This meant developers had to get creative, either duplicating data or manually resolving references between records, which could get messy quickly.
So it was a choice between potentially inconsistent data or writing a ton of extra code to handle the relationships. Neither option sounds ideal.
Exactly. And this brings us to a crucial point. Understanding the trade-offs of different data models is a must-have skill for senior engineers. There's no one-size-fits-all solution. And recognizing this is key for acing those interview questions.
That makes perfect sense. So when I'm in that interview, I should be ready to discuss the pros and cons of both relational and document databases, especially in the context of the specific problem being discussed. It's not just about knowing how to write SQL queries or using a particular NoSQL database. It's about showing I understand the bigger picture of data modeling.
You got it. Being able to explain when to choose a relational database and when a document database is a better fit demonstrates a deeper understanding of data modeling principles. And that kind of insight can really set you apart from other candidates.
Okay, so we've talked about SQL, NoSQL, the impedance mismatch, and even taken a quick trip back in time to those early database systems. Where do we go from here?
Well, next we'll dive deeper into the concept of schema flexibility and see how it plays out in both relational and document databases. This is another area where understanding the nuances can really impress your interviewer.
All right, so let's talk about schemas. It seems like schema flexibility is often touted as a major advantage of document databases, but I'm curious, how does it actually work in practice?
Well, think about it this way. In a relational database, you define your schema up front, tables, columns, data types, everything very structured.
Right.
It's kind of like static typing in programming languages where the compiler checks if your code sticks to those types.
Okay.
This is what we call schema-on-write. The structure has to be defined before you can even write data to the database.
And that makes sense in a lot of cases, but then you have document databases, which seem to be, a bit more relaxed about things.
Exactly. With document databases, you don't have to lay out this rigid schema beforehand. You can just start adding documents, even if they have different fields. Yeah. It's more like dynamic typing in programming languages, where the type checking happens at runtime. This is schema-on-read. You figure out the structure as you access the data.
That sounds pretty flexible. But could that lead to, a bit of chaos? What if different documents in the same collection end up with totally different structures? Wouldn't that be a nightmare to manage?
That's a valid concern, and it's where understanding the nuances of schema flexibility is crucial, especially for a senior engineer role.
Right.
While document databases don't enforce a strict schema at the database level, there's usually this implicit schema embedded in your application code.
Okay.
The code that's responsible for reading and writing data, it still expects a certain structure, even if it's not explicitly defined in the database itself.
So it's like having a schema, but more like a guideline than a hard and fast rule.
In a way, yes. Now, to answer your question about potential chaos, let's say you need to change how you store user data. Maybe you initially had a single name field, but now you want separate fields for first name and last name. In a relational database, you typically have to go through a schema migration, alter the table, update existing data, and all of that. This process can be time-consuming and might even require downtime.
Oh, I've been there. And those schema migrations can be such a pain. You have to plan everything out so carefully.
Right. Now imagine handling the same scenario in a document database. You can often just start writing new documents with the updated structure.
Wow.
While your application code gracefully handles both the old and new formats when reading data, For example, it might split the name field into first name and last name on the fly.
That's pretty slick. So it seems like schema flexibility can be a big advantage in environments where things are changing quickly and you need to adapt fast.
Absolutely. But of course, there are always trade-offs.
Right. No such thing as a free lunch.
One potential downside is the risk of data inconsistency. Without a strictly enforced schema, it's easier to end up with documents in different formats, which can make querying and processing data less reliable. It also increases the potential for introducing errors, Accidentally using the wrong field name won't be flagged by the database, for instance.
So there's less of a safety net when it comes to data validation, which could be a big concern in certain situations.
Exactly. Schema flexibility is a powerful tool, but it needs to be used thoughtfully. There are scenarios where a well-defined schema is critical. If you're dealing with sensitive financial data, for example, you'd probably want the database to enforce those strict data validation rules to ensure accuracy and integrity.
Yeah, that makes sense. And I've heard that there are ways to introduce schema validation even within document databases.
You're right. Some document databases offer tools for schema validation, and you can always implement validation checks at the application level. The point is that senior engineers need to understand these various approaches to schema management and make informed choices based on the specific needs of the project.
It's about choosing the right tool for the job and understanding the implications of your choice.
Precisely. And remember, the world of relational databases isn't standing still either. Many now offer support for JSON documents, allowing you to have some of that document-like flexibility within a relational structure.
So it's not an either-or situation anymore. You can kind of have the best of both worlds.
Exactly. The takeaway here is that a senior engineer should be comfortable navigating these different approaches, recognizing that each has its own strengths and weaknesses.
Now I want to shift gears a bit and talk about performance. Document databases are often praised for their performance advantages, particularly when it comes to data locality. What's the story there?
Well, document databases typically store an entire document as a single unit. This means that when you need to fetch a whole document, it's already together on disk, which reduces the need for disk seeks and leads to faster retrieval times.
So that sounds like a big win for performance, especially for applications where you frequently need to access entire documents. But are there any downsides to this approach? Because, there are always trade-offs, right?
Of course. One trade-off is that even if you only need a small piece of information from a document, the database might still load the entire thing into memory, which can be inefficient, especially for large documents.
So it's kind of a double-edged sword, fast when you need the whole document, but potentially wasteful if you only need a small part. Are there any other performance considerations to keep in mind?
Yes. Updating documents can also be less efficient in some cases. If you need to change a single field, the entire document might need to be rewritten to disk. And this can become a bottleneck, especially if updates are frequent.
So data locality is another area where there are trade-offs to consider.
Absolutely. And just as relational databases are incorporating JSON support, they're also making strides in data locality. Some offer features like nested tables or column families, which allow you to group related data together for better performance. It's like the two worlds are borrowing ideas from each other.
It seems like the lines between relational and document databases are becoming more and more blurred.
Indeed. We're seeing a convergence of concepts, with both types of databases incorporating features from each other.
So for someone preparing for a senior software engineer interview, what's the key takeaway from all of this?
I'd say it's this. Understanding the trade-offs associated with different database models and the factors that drive their evolution is crucial for making those informed design decisions.
It's about seeing the bigger picture, recognizing that technology is constantly evolving, and being able to adapt to new challenges and opportunities.
Precisely. Now, to round out our discussion, we should talk about how these different data models tackle those intricate many-to-many relationships. That's another common interview topic where understanding the nuances can give you an edge.
Okay, so let's get into how different database models handle those complex many-to-many relationships. The scenarios where multiple records in one table are connected to multiple records in another, like authors and books. One author can write multiple books, and one book can have multiple authors. It's easy to see how those relationships can get tangled up really quickly.
Absolutely. And relational databases handle this really elegantly with the concept of joins, specifically join tables. In your author book example, you'd have a separate table called author book that simply stores pairs of author IDs and book IDs. It acts as a bridge, linking the two main tables without duplicating data, which helps maintain data integrity.
Okay, that makes sense. The join table acts as this neat intermediary. But we talked earlier about document databases and how they historically struggled with joins, even bringing up those older hierarchical models like IBM's IMS. So has anything changed? How do modern document databases handle this?
Well, document databases have evolved, but the fundamental challenge of representing those many-to-many relationships within their document-centric structure, it still kind of persists. Remember, document databases prefer to store related data together within a single document. So when you have many-to-many relationships, you have a few options, each with its own trade-offs.
Okay, let's hear about those options.
One approach is to embed the related data directly within a document. In our author book scenario, you could store an array of book IDs within each author document, and vice versa. This approach works well if the relationships are fairly simple and you frequently need to fetch all the related data at once.
So it's like having a miniature library embedded within each author document, making it quick to access an author's entire bibliography. But I imagine updates could get kind of tricky. What if a book gets a new edition? Do you have to update every single author document that references that book?
That's a great point. Updating embedded documents can become a real headache, especially as your dataset grows. You might end up updating tons of documents, which can impact performance.
Sounds like we've hit another trade-off. What are some other ways to approach this?
Another common option is to use references, kind of similar to foreign keys in a relational database. Instead of embedding the entire book data within the author document, you would simply store an array of references, those document ideas that point to the related book documents.
Okay, so instead of storing all the details about each book, you're just storing a pointer to the relevant book document. That seems like it would simplify updates, right?
Exactly. If a book's information changes, you only need to update the book document itself. This approach avoids data duplication and makes updates a lot more efficient.
But wouldn't this approach lead to more queries? You'd have to fetch the author document and then make additional queries to retrieve each book that's referenced in the document. That could slow things down, especially if you have a really complex network of relationships.
That's right. Using references can lead to more queries, which can affect performance, especially in high-traffic applications. It's another one of those classic trade-offs, denormalization versus multiple queries.
It seems like there's no perfect answer. Choosing the best approach really depends on the context of the application and the types of queries you're performing.
You got it. And here's where things get even more interesting. We're seeing this kind of convergence of ideas. Some document databases now offer better support for joins or allow you to define relationships between documents, bringing them closer to the relational model. And on the other hand, many relational databases have embraced JSON and offer more flexibility within their structured schemas. It's becoming less about choosing a side and more about picking the best features for the job.
It's almost like the database world is acknowledging that both relational and document models have their strengths.
Absolutely. And that brings us back to a key point we've been emphasizing throughout this entire deep dive. As a senior engineer, you really need to understand these trade-offs. You need to be able to articulate when a relational database might be a better fit and when a document database makes more sense. Showing that you can think critically about data and make those informed decisions is a huge asset in those senior level interviews.
So, to all of you aspiring senior software engineers out there, as you get ready for those interviews, keep this in mind. Show those interviewers that you're not just a code monkey. Show them that you can think critically about data, and you'll be well on your way to landing that dream job. We've only scratched the surface here. What other aspects of data model evolution do you find interesting? Let us know. We're always up for another deep dive.